Welcome to the NHERI SimCenter's live expert tips. In this session, we will introduce you to new features in the Regional Resilience Determination tool. Our expert today is Dr. Jinyan Zhao. Jinyan is a postdoctoral scholar at UC Berkeley and software developer at the NHERI SimCenter. He received his Ph.D. from the Department of Civil and Environmental Engineering at UC Berkeley, where he studied numerical simulation and risk assessment of large-scale civil infrastructure in underground construction. At the SimCenter, he is developing and benchmarking capabilities for regional-scale risk analysis resulting from natural hazards. Jinyan, thank you for being here.
Thanks, Matt, for introducing, and hi, everyone online. I'm Jinyan, and today I'm going to introduce some new features in R2D, the Regional Resilience Determination tool. And today I'm going to cover three topics. The first, I will give you an overview of the Regional Resilience Determination workflow in R2D. I will spend about 10 minutes on this. It's a long introduction, but it's sort of a prerequisite for what I'm going to present later. And after the overview, I will introduce a relatively new feature in R2D, the Earthquake Event Generation tool. This tool helps our users to generate ground motion intensity and tap history on a regional scale. And this generated ground motion can be applied in the later seismic performance assessment. And in the end, the third topic is a seismic performance assessment for transportation infrastructure. Transportation infrastructure is a new type of infrastructure that we recently included in R2D. So now let's have an overview of the regional resilience determination workflow in R2D. R2D aims to help our users to perform this regional scale simulation workflow from asset definition, hazard definition, modeling and analysis of infrastructure, damage and loss analysis of infrastructure after natural hazards, and the recovery simulation after natural hazards. From this plot, you can see all the hazards and asset information and response recovery information. They are spatially distributed. So in R2D, we embedded the GIS software QGIS to help us visualize and manage this information on a regional scale. And natural hazards are inherently uncertain, and the modeling of infrastructure on a regional scale may also suffer from big uncertainty. So along the process, we focus on capture the uncertainty by uncertainty quantification techniques. R2D supports multiple types of hazards, and it also supports multiple types of assets. And more importantly, R2D is a very flexible workflow. So we use these puzzle pieces to represent our workflow, because if I'm not happy with one model I'm using in one of the steps in this workflow, I can take out this puzzle piece, get another model that I like, and plug it in, and I complete this whole regional simulation workflow. Taking the modeling and analysis part as an example, if I am given a building like this is one of my regional building inventory, I could use these fragility curves to get the building damage state directly from the hazard intensity measure. These fragility curves are usually come from famous hazards, so this kind of analysis is called hazard-style analysis in our vocabulary. Hazard-style analysis is simple, it's fast to perform, but it may suffer from big uncertainty. So instead, I could use a multi-degree freedom system to simulate my structure and get the story drift of my structure. And if you still think that's a low fidelity model, you can also use high fidelity OpenSys nonlinear history analysis to simulate the response of our structures. And further, we can also use surrogate model to accelerate that process. So all four types of these models can be plugged in here in the modeling and analysis step of the workflow to enable a flexible option. And all the other steps in this workflow, there are also many options allowable in R2D. So with this flexible workflow, R2D can be used in many custom use cases according to the needs of our users. So this is an introduction of what R2D does. And if we have a closer look at this workflow from a user's perspective, to use this workflow, they need to define which operation they want to perform in each step of this workflow. Starting from the asset definition, the user needs to input R2D inventory, asset inventory. In the inventory, the information required by the modeling and analysis procedure afterwards needs to be included. After defining the inventory, the user also needs to define the hazard event they would like to study. Typically, the hazard event is defined in the format of intensity measures or time history on a switch of grid points. And R2D will do a spatial interpolation between the grid points to get the hazard level at a specific infrastructure location. Given that hazard level, R2D will perform modeling and analysis of the infrastructure based on the option that the user selects. For buildings, we have automatically generated multi-degree freedom models to simulate the building response, and we also allow users to use any OpenSys or any custom Python script as their structural modeling and analysis engine. And the output of this modeling and analysis procedure are engineering demand parameters, or EDPs. And in earthquake engineering, these EDPs can be story drift. Given such EDPs, we can go to our damage loss analysis to determine damage measures such as damage state and decision variables such as economic loss or repair time. And in the end, this recovery part is something we are still under development. We are working on incorporating a recovery simulation to study the recovery state after each time steps of a natural hazard event. So this is how the workflow works in R2D. I would also introduce how the workflow is implemented behind the scene. So as a SimCenter user, you will sit on top of here and you interact with our graphical user interface. We call it the front end. And after you select the operations you want to perform in your workflow, you hit this run button. The front end will wrap up all the information you input to R2D and write it into this input RView JSON file. And then this JSON file will be fed into R2D backend driver rview.py. This is a Python script that parses the input JSON file, does some setup of the working environment, and runs the workflow. And in turn, this workflow will run multiple applications on your computer. And such applications can be Dakota for uncertainty quantification, and it can be OpenSys for structural analysis, and many C++ and Python scripts that we created at SimCenter to perform different workflow in the puzzle pieces. And along the process, both the front end and backend may interact with online cloud resources to get additional support, such as we will download data from peer NGA's ground motion database, and we also download infrastructure inventory data from National Highway Administration's database. What I introduced so far is how we run assessment, run analysis on your local computer, and R2D can also run your job on a high-performance computer provided by DesignSafe. DesignSafe is physically located at Texas Advanced Computational Center. And if you want to run analysis on their high-performance computer, instead of sending the input JSON file to your local backend driver, we will use Tapas API to wrap up all the input information, including the hazard definition files, asset inventory files, and your input JSON files, send it to DesignSafe's high-performance computer and run the backend driver on their HPCs. After the analysis is completed, they will save the results on their server. And as a user, we can interact with DesignSafe's website to retrieve the analysis result. So this is a quick summary of how R2D is implemented. And if you'd like to learn more about this, you are very welcome to go to our website. On our website, you will find links to download our apps, links to our documentation, and also there is a link to join our SimCenter forum. And you can post your questions or you can request some features through our SimCenter forum. And most importantly, all of our codes are open source, and the front end and the back end, they are publicly available on these two GitHub repo. And if you would like to, you are very welcome to look into the code to understand how things really work behind the user interface. Also, you are very welcome to extend these tools to create your own version of R2D. And if you need any support, please feel free to reach out to us through SimCenter's forum, and we are ready to provide support. So that wraps up our first topic today, overview of the regional resilience determination workflow. Now let's have a look at the second topic, the earthquake event generation tool. So looking back to this simulation workflow in R2D, the earthquake event generation tool falls in the second step, the hazard definition. It helps a user to generate the intensity measure information on a regional scale, and they can use that as the input to their later analysis. At SimCenter, we define regional earthquake assessment use cases into two groups. The first group is specific earthquake scenario applications, where the user, they know a specific earthquake rupture scenario in their mind. They know the magnitude of the earthquake, they know the geometry, the location of the rupture, and they want to study the effect of this rupture to a region nearby. In contrast, a user may want to learn all the possible scenarios or rupture scenarios in a region, and they want to study the overall hazard and the overall risk. Both of these two groups of use cases are accomplishable in R2D, and I will introduce how to accomplish them in this presentation. We further divided, for specific earthquake scenario applications, we further divided it into more specific use cases. The first two use cases are relatively simple. They are the cases when the user have their own intensity measure or time history, ground motion time history defined on the region. And if they want to use this ground motion as the input to their assessment, they could just load it to R2D by preparing an event grid file. This event grid file will define the location of a set of grid points, and for each grid point, the user also needs to prepare a grid point file. This grid point file contains a list of intensity measure or a list of time history records in this SimCenter's time history format. After R2D loading this information, it will interpolate between the grid points to get the ground motion intensity at specific building, and then do the subsequent analysis. So this use case may be the case when a user have their own physics-based ground motion simulator, or they have a stochastic ground motion model, and they have the capability to generate ground motion on a regional scale. However, more commonly, a user may only have an earthquake source model in their mind, and they want to use the empirical ground motion models to generate ground motions. And that's when this earthquake event generation tool comes in. In this earthquake event generation tool, we implemented 3 types of earthquake source models that we think are most commonly used by earthquake engineering community. The source models are the Uniform California Earthquake Rupture Forecasting Model embedded in OpenSHA, any earthquake source model defined in OpenQuakes format, or a point source model, which is usually used to simulate the background earthquakes. And the workflow of this earthquake event generation tool is, given an area of interest, I need to first define the grid point locations and the geological conditions at the grid points. After that, I define the earthquake source model, which is typically all the earthquake faults nearby this region. And then I will select ground motion models and spatial correlation models to generate intensity measures or spectrum at each grid points. And then if I need time history in my analysis, I can also use R2D to select records from peer NGA database to get a large number of ground motion records on a regional scale. So now let's stop this slideshow and have a little demonstration of how this earthquake event generation tool works. So if you open R2D, this will be your main user interface, and the earthquake event generation tool will be accessible from this tools drop-down menu. If I click this earthquake event generation, this is where I define the grid point locations. I will define the grid point locations by providing R2D CSV file that I prepared beforehand. In this CSV file, I defined the longitude and latitude of a set of grid points. I also defined the VH30 and the basin depths at the grid points. Since I defined them in my CSV file, I will select user specified for VH30 and basin depths. And if you do not have this information beforehand, you could interpolate the VH30 value from some local or a global geological database built in R2D. After defining the sites, I need to define my earthquake source model. As I said, we implemented 3 types of earthquake source model, and in this demonstration, I will use OpenSRA as an example. In OpenSRA, we implemented the Uniform California Earthquake Rupture Forecasting user version 2 and version 3. Version 2 has relatively less number of rupture, so for the sake of time, I will use the simpler version of user, and you are free to use user 3 if you would like to use the updated earthquake rupture models. Here are some other parameters you can define if you want to include background seismicity and how you want to treat the background seismicity. And here we can define what's the maximum distance from an earthquake fault to my site that I would like to consider. To save some time, I will not include a large number of earthquake rupture. I will only look at the ruptures that are 50 kilometers within 50 kilometers from my site. And I can also define the range of earthquake's magnitude that I'm interested in. Because the small magnitude earthquakes usually do not impose big hazard to our structures, so I will only select the ruptures that are larger than magnitude 5.5. After I defining this, I will hit this forecast rupture scenario button, and R2D will run a process in the background. Here you can see some outputs from this program output dialog, and after the analysis complete, it says 383 ruptures is loaded to R2D. And these 383 ruptures are all the ruptures close to my site and satisfies my selection criteria. And if I go back to this earthquake event generation tool model, if I zoom into this layer, I could visualize all the earthquake rupture. This is a nice way to visualize the rupture, and it's also a nice way to select which rupture is interested for you in your later study. And to generate earthquake ground motion field on a regional scale for scenario-specific applications, you need to select the earthquake rupture scenario that we just generated. So R2D also load in the generated rupture to this tabular format, and we can have a look at the rupture that we would like to study. For example, I want to study this rupture on the Hayward fault with a magnitude 7 with this mid-90 rate. I can just click on this rupture and select it, and then I can go to the next step to define which intensity measure I want to generate through this empirical ground motion model, and define which and select which ground motion model I would like to use. We implemented the 4 peer NGA-2 ground motion models in R2D. Also, I can select the spatial correlation models to define the joint distribution of the intensity measure in this region. After selecting this, I can go to record selection. If I want time history records, I could select peer NGA-2, and since the ground motion models only give us intensity measures, and we can select time history records to match the intensity measures generated by ground motion models. But record selecting and downloading may take some time. So in this demonstration, I will stop by getting intensity measure. I will not select any records from the database. And if you need time history in your analysis, feel free to do so afterwards. And in this box, this is where we input the number of ground motion we want to generate. As I said, the ground motion models gives us the median and standard deviation of intensity measures, and the spatial correlation gives us the joint distribution of the intensity measures. However, to perform regional seismic performance, we need realizations of these intensity measures, these ground motions. And here is where we define how many realizations we are going to generate from the joint distribution. Again, for the sake of time, I will select a small number of ground motions, 3, but typically an earthquake engineer may need 10 to 20 ground motions per set to capture the variability of the ground motion. Now I will hit this Run Hazard Simulation button. Again, R2D will run some code in the background. And when it finishes, its R2D will output earthquake hazard simulation complete, and we can see the results in this working directory. So now if I go to my R2D local work directory in my documents directory, hazard simulation, go to ground motions, outputs, we will be able to see the ground motions that we just generated 1 minute ago. And inside these IMs, you would be able to see an event grid file and the grid point file containing the intensity measure at each grid point. And these files would be ready to use to load back to R2D to do regional seismic assessment. So that wraps up the first demonstration today. I will go back to my slideshow to show you another use case of regional earthquake assessment in R2D. This is the case when a user wants to study a historical event, and very likely this user may go to USGS shake map to get the ground motion intensity information. So in R2D, we also allow the user to give us a USGS shake map grid file, and we will convert that into grid points and the SimCenter ground motion format, and to use that in our later seismic assessment. So far I have covered the specific earthquake scenario use cases, and the probabilistic hazard analysis is also possible in R2D with this earthquake event generation tool. So in probabilistic hazard analysis, we are not limiting us to a single earthquake rupture, but we need to study all the possible rupture in a region. And we can do that with this conventional Monte Carlo simulation way, where instead of selecting one scenario, we will select all the scenario in the region and repeat the scenario-specific workflow by very many times. And as you can imagine, that will generate a very large number of ground motion maps, and it is not possible to get the structural response for each of those ground motion maps. So in R2D, we also implemented optimization-based downsampling algorithm to select a subset of the earthquake scenarios, but we scale up the occurrence rate a little to keep the overall hazard level as the same as the full set of earthquake scenarios. Here is a visualization of the hazard curve produced by the subset of the simulation and the full set of the simulation. There are some discrepancy at the very low ground motion intensity, but those intensity may not impose risk to our infrastructure. And there are also discrepancy at the very small probability events, and those events are not of our engineering significance. So as you can see, the subset of the simulation can only needs dozens of earthquake scenarios in contrast to the thousands of earthquake scenarios, and this will significantly reduce our computation time. And if you'd like to learn more about this, you are very welcome to go to our documentation, and you're also welcome to read this original paper. Just a summary of this earthquake event generation tool. In this part, we demonstrated how to use the event generation tool to generate one or multiple earthquake events and the corresponding ground motions. And the generated ground motions can be used in later regional seismic performance assessment. That wraps up our second topic today, the earthquake event generation tool. Now, let's have a look at our final topic, performing seismic performance assessment for transportation infrastructure. Again, going back to this simulation workflow in R2D, this is the general workflow for any type of infrastructure, both hurricane or earthquake hazards. But to perform earthquake events simulation for transportation infrastructure, we need to make some specific selections. First, in the asset definition part, we need to load in transportation infrastructure asset to R2D. And we can generate this transportation infrastructure inventory with a tool called Brails built in R2D. Brails interface with the National Highway Administration's database, and it will download the National Bridge Inventory, National Tunnel Inventory, and the National Roadway Inventory, and convert that into SimCenter's format and load it and save the specific region, the inventory in the specific region defined by the user on your local computer. And you can load the inventory to R2D for your regional assessment. After defining the asset, we need to define the hazard. For transportation infrastructure, the roadways are very sensitive to ground deformation related hazard. So very likely you want to include permanent ground deformation PGDs in your hazard definition. And then in the modeling and analysis part, currently in R2D, we only support hazard style analysis for transportation infrastructure, which means we get the damage state of the infrastructure directly from hazard intensity measure. But if we would like to, it is also possible to use OpenSeas or custom models with some interaction and extension to our backend code. So after modeling and analysis, we could use fragility curves and restoration curves defined in FEMA hazards to get the damage state and the recovery time, economic loss for each of the transportation infrastructure components. And we are also working on integrating a traffic flow simulator in R2D so we can study the network level performance, such as what is the average travel delay time after an earthquake event. So this is the workflow of performing seismic performance assessment for transportation infrastructure. And now let's have a demonstration of how it works with our software. By the way, in this demonstration, I will introduce how to generate transportation inventory with rails. And then I will demonstrate how to run hazard-style seismic performance assessment for transportation infrastructure. Again, if I open the main user interface of R2D, rails would be accessible from here, from this tools drop-down menu. And if I click this rails transportation, I will open the window for rails. Here I will define a bounding box, and rails will collect all the roadway information, bridge information, tunnel information inside this bounding box from National Highway Administration's database. And because the roadways can be very long, and it is difficult to map the intensity measure applied on this map because intensity measure are spatially variable. So in R2D, we will discretize the roadways into smaller segments. And we would assume the intensity measure on the smaller segments would be relatively uniform. And the default value for this roadway length is 100 meters, but you are free to select a longer or shorter roadway in your inventory generation. So after defining this bounding box and the roadway discretization length, I can hit this button, and R2D will run rails in the background. After the analysis completes, we can see the output says the inventory information is available in this rails folder. So now if I go to my documents, R2D, local working directory rails, I would be able to see this inventory that we just generated. We could use this inventory to R2D in the second part of our my demonstration today, which is transportation infrastructure assessment and earthquakes. But this inventory is only contains the information for a small region, and so instead, I will use one of our built-in example 14, to show you how to perform this assessment for transportation infrastructure. So in R2D, we have a series of built-in examples, and each example corresponds to one of the typical use case that we think R2D can be used to. And in this demonstration, I will use example 14, the basic hazard-style transportation assessment. If I click that example, R2D will load in the user input, and what you see in this user interface would be the same as if you do the selection step. You do the selection and input the inventory and hazard file step by step. So now let's have a look at this user interface and what we need to select to perform transportation assessment. In the first tab, we have general information. This is where we define the units we want to use in the assessment. And in the asset layers, I will select buildings and transportation. So in this assessment, I will study both buildings and transportation infrastructure. And here I will select which kind of outputs I want to save. I will save the engineering demand parameters, the damage measures, and the decision variables for each of my building and transportation component. In the next tab, we need to provide R2D with a set of hazard information. In this example, we generated this hazard information containing ground shaking intensity measures and ground failure intensity measures beforehand. And if you have your own set of hazard information, you could prepare them in SimCenter's format and load in R2D to perform your own assessment. After we provide R2D with these intensity measure files, R2D will parse the files and detect which type of intensity measures are provided. And for each of the provided intensity measures, we need to define the units we defined in those intensity measure files. After defining hazard, we need to define asset. The asset, because we included both buildings and transportation in this example, we need to provide one asset file for the buildings. And the information includes number of stories, year built, occupation class. These are the information necessary for hazard style analysis. And for transportation, in this inventory GeoJSON file, we defined three types of infrastructure, three types of transportation infrastructure, which are bridge, roadway, tunnel. And for each of them, they contain different set of information. For bridges, we need to define bridge class, maximum span length, number of spans, and those informations are used later to define which fragility curves in hazards menu that we will use to analyze this specific bridge. And similarly for roadways, we defined the road type and number of lanes, maximum speed limit, and this information are used in the future for our traffic flow simulator. So after defining the hazard and asset, we will go to this tab, HTA, that stands for hazard to asset mapping. So in R2D, we use a nearest neighbor algorithm to do the spatial interpolation to interpolate the ground motion intensity at grid points to the specific infrastructure location. And next, in the modeling and analysis part of this workflow, because we use hazards fragility curves to get damage state directly from intensity measure, modeling and analysis are not required, so I will leave them as default. And the next step in this workflow is damage and loss analysis. The fragility curves for transportation infrastructure are implemented in Pelican version 3. And Pelican version 3 also have several options for damage and loss method. For buildings, if I have the story level engineering demand parameter, such as story drift, I can select this hazard story-based earthquake fragility curves. For us, since we only have intensity measure, I will use this intensity measure-based hazard fragility curves. And if you are studying hurricane, we also have hurricane-related fragility curves, and we also allow you to give us your own library of fragility curves. But for our demonstration, I will select intensity measure-based fragility curves. And here I will check this box to include ground failure. This is because I included PGD, the permanent ground displacement, in my hazard definition tab. So I could study the damage caused by ground settlement and lateral spreading on my infrastructure components, such as roadways, bridge, and even buildings. So this is how we define the damage loss analysis in this workflow. The next two tabs are uncertainty quantification and random variables. These two tabs are used when we have uncertainty in our structural analysis model. Taking buildings as an example again, if I have a multi-degree freedom to simulate one system to simulate one building, and that is a big simplification of the building into a multi-degree freedom. So I may want to define some uncertainty at the story stiffness and the story damping to capture this uncertainty caused by this huge simplification. And if I want to define that, I will need to use this uncertainty quantification and random variable tabs. But since in this demonstration for transportation, we do not have any structural analysis model and analysis, I will also leave this UQ and RV tabs blank. And here is the results. Because running all this analysis may take a long time, I run the analysis beforehand, and I can show you how the results will look like. So here will be the results if you run the analysis for all the roadway, all the transportation infrastructure. You would see a distribution of the damage state of the roadway. Similarly, for bridges and tunnels, each of them may suffer from different damage state. And on the right-hand side, you can see a summary of the mean repair cost, repair time for each of the infrastructure. As for roadways, they are here. Bridges, they have their own tab. Tunnels, they have their own tab as well. And in these tabs, you can see the mean repair cost, mean repair time. Also, you can see the standard deviation of them. And this is just meant to give you a sense of what is the uncertainty in this analysis. So that wraps up this demonstration for transportation infrastructure assessment. As a summary, in this part, we generated transportation inventory with Brills. And then we run hazard-style seismic performance assessment for transportation infrastructure. And beyond hazard-style seismic performance assessment, customized models and workflows is also possible to be implemented in R2D by interacting with R2D backend. And if you would like to use this feature, please contact. And if you need any supports, please feel free to contact us. And if you have your own customized model that you would like to popularize with SimCenter platform, you are also very welcome to do so. We look forward to hearing from you. So that is the end of my topics today. Before I stop, I want to point you to some more resources. Here are the links to our website, to our GitHub repo, and to our forum, where you can post questions and request features. And also, we will be at the NHERI Natural Hazard Research Summit in May this year, and there will be a series of consultation and workshops. We look forward to meeting you there. And here is how our forum look like. If you have any questions, feel free to reach us at the SimCenter forum. We look forward to hearing from you. That's the end of my presentation. Thanks everyone for.
Sorry, thank you very much, Jinyan. That was very, very detailed. There was a lot of information, but I appreciate you covering both the transportation inventory generation as well as the earthquake event module. I think one question that came up is the examples that you showed one of 14 examples in R2D. Where do we find out more about those examples or what's included in them?
The description of the examples can be found in our documentation. And the source files, such as the input hazard files, the input asset files, they are available on our GitHub page. In our GitHub, there is a specific repo called R2D examples, and all the source files are stored there.
Great. And another question about the input files and saving them. If somebody has generated an inventory for the transportation network, how do they then come back to the input file to run a simulation later or change some variables and run something a different case?
Yeah, so R2D user interface does support the user to save all the input they provided to R2D. So if they go to this edit, file and click the save R2D, and they define the path of where they want to save the file. R2D will gather all the user input and write that into a JSON file and save it to be ready to load in later process. So if you are halfway of defining your workflow and you want to reproduce that later, you could use a save feature. And later, if you want to load one file that you just saved, you can go to this file and click open and select the file you saved, and R2D will reproduce what you input to R2D before.
Great. Well, I want to say thank you again for the presentation. Thank you to the attendees who've joined us this morning. And I want to remind people that they can register for future upcoming live expert tips by going to our webpage, which is simcenter.designsafe-ci.org. This concludes today's live expert tips with the NHERI SimCenter. We hope you've been inspired to pick up these modules that Jinyan shared and adapt their capabilities into your own research. So again, thank you very much, Jinyan.
Thank you. Thank you, everyone.